Thank you all for joining this webinar. Great to see you all. Quite exciting for us. Quite some time ago since we had our last edition of our webinar. And I think everybody is kind of familiar with the concept. We always used to give our customer base a platform to present their scientific results with PLD. But today, a bit of a different topic, as you have seen in the program. So for quite some time now, we have been teaming up with the recently founded company 3Wave Instruments from ETH Zurich in Switzerland, who has been developing a new in situ diagnostics tool based on second harmonics generation, bringing it truly from lab to a commercial product. And we're actually super excited to present this now for the first time to a wider audience, to you as our PLD customers, as it is potentially a very nice and interesting tool to integrate on your on the PLD solution. So we really want to tell you everything about it today. Bit of housekeeping. Feel free to ask questions anytime through the Q&A or chat. So we have three contributions and presentations, and after which we hopefully can have a nice interaction and discussion. So I'd like to give the word to Marcus Dantle. He is the co-founder of the 3Wave Instruments company, and he will give a brief introduction on the speakers, on the topics, and so Marcus, feel free to share your screen.
Good morning, everyone. My name is Marcus Dantle. 3Wave Instrument is actually founded by 5 people with 2 different backgrounds. So we have the scientific founders. It's Manfred Fiebig, Morgan Rossi, Janis Lehmann. I mean, those are the people who work at ETH Zurich. I mean, they have invented the system, they have built it, and this lab prototype is up and running since 2021, so for more than 4 years. And well, it runs in the lab at the moment. And by coincidence, Manfred and I, we have met each other 1998 in Tokyo, in Japan. We always stayed in contact. But I then worked those 27 years in the industry, where I've also got to know Jens. And we bring in here this industry experience, you know, how to bring a prototype to the market, what's needed, which kind of certificates, and all, you know, the small things to get this company up and running and deliver a good quality product to the market. So this is the short introduction of our team. And now let's start with the real interesting thing. And I would like to hand over to Manfred.
Hello, everyone. Great to see so many of you. And I'm the leader of the laboratory for multifunctional ferroic materials in the Department of Materials at ETH Zurich. And I will begin with a little bit of science on the product that we are now selling. So the scientific background. And Oh, okay. So just give me a minute. Good. So that's where we start. So what we do is we combine thin film growth and in situ optical probing. Well, it's not the first tool that we would offer here. So we possibly all know READ. So that with an electron gun, while you grow a thin film with pulse laser deposition or even MBE, you see that you neatly put atomic layer on atomic layer by sending in an electron beam, and that sees neatly that your structure grows crystallographically as you want it. The problem is you see that it grows nicely in terms of atoms, but what you do not see is it really doing what you want while it grows, or that does the functionality emerge that you want? So how do you see that? And electrons do not do this, so they cannot see if something becomes ferroelectric or ferromagnetic or magnetoresistive or whatever. So there we were seeking for a way out to close this gap. And our reasoning was that we said, okay, we want to image ordered structures and their functionality. So imaging implies something optical. So let's think about an optical technique. We also want to see ordered states, symmetry breaking, and what it does in terms of functionality. So something that is very sensitive to symmetries is nonlinear optics. So that was then basically the technique of choice to somehow involve as a new in situ tool. And what we then opted for is what we have been doing here for many, many years, namely nonlinear optics in the form of optical frequency doubling or second harmonic generation. So what you do is you send in an electric light wave into a material, and we all know electric fields cause polarization. And if the field is strong enough, you do not only get proportionality, so you would get a polarization contribution that goes with E square or e to the third power, as shown down here. So and these contributions are higher order. They require strong fields like from a laser. If I take the first of these contributions, so the E square contributions, then you see that because of the frequency dependence of the electric fields, then with 2 photons here, 2 fields here, you get a frequency doubled component as polarization. You can also see it in the picture. So you kick your electrons twice to bring them up here, and then the relaxation is in a single step. So you send in omega light and out comes 2 omega. Yeah, so this is called optical frequency doubling or second harmonic generation, and it's a very symmetry selective process. For example, to see it in this leading order that is shown here, inversion symmetry needs to be gone. So that immediately implies that it's a great tool to see ferroelectric order, because that's what ferroelectric does. It has an off-center movement of ions with respect to other ions. That creates an electric dipole moment and an electric polarization, but it also breaks the inversion symmetry. So right when this happens, when your material becomes ferroelectric, you see the emergence of this frequency doubled signal out of zero background. So it's a higher order weak process, but it's background free. So you can crank up your detector and you see it. So strong light or intense light is not always good if it's on the background of other intense light, but here it's background free. And that doesn't only work for electric order, it also works for magnetic order. Little example here. So if you take this chain of ions and you put spins on that, pointing down, up, that also breaks the inversion center of the material. So background free again, you see another second harmonic component emerging that indicates magnetic order. And you can do both in the same experiment. So here we see that we send in light at omega. On the sample, it gets frequency doubled. You dump your omega light, and then you analyze the frequency doubled light. And because electric magnetic order breaks symmetries differently, you see differently polarized frequency double contributions. One tells you about the electric order, one tells you about the magnetic order. So this is very neat, and it's all background free. This is the real big advantage. Okay, so then we are back to our original sketch. So how do we see the functionality of the film while it grows? And that would now be by sending in addition to the electron beam, we send in a light wave, a laser light at omega, nicely from the distance through the windows, non-destructive, non-invasive, and what you get back is the frequency double light, and that tells you about any type of order you have in your material. You can see buried states, order while functionality while it emerges. So that sounds nice as a scientific concept, but what does it really mean in terms of equipment? So what did people do before this idea came up? So what they would do is they would grow a sample, say a ferroelectric sample, and they don't know when it becomes ferroelectric. So what they do is they stop the growth after 5 unit cells, 10 unit cells, 20, 75, take the sample out of their chamber, measure the ferroelectric properties, and then they see, oh yes, at 5, 10, 20, 75 unit cells, it's ferroelectric. Somewhere it will not be ferroelectric anymore. That's tedious. So you need to grow a sample, terminate the growth, take it out, characterize it. And that takes about 1 day per data point. So 4 days work for these 4 data points. And then it's still indirect because you do not measure the sample while you have it in your chamber, but you take it out and then you characterize it and so forth. And you have 4 different samples. Now, our approach is to do this while the sample grows. And here we see we get 100 data points in 20 minutes. So it's a speed up factor with many zeros. And you immediately see if you grow a ferroelectric bismuth ferrite film at the 4th unit cell, this frequency doubled signal emerges. So here it gets ferroelectric, sample becomes ferroelectric. And then when you have like 12 unit cells, you have the saturation. So from here, the film is like a bulk crystal. And yeah, consider the timescales, 4 data points, 4 days versus 100 data points in 20 minutes. And really the one sample, not 4 or 100. Good, so that was the idea for our spin-off, to convert this into a marketable device. Here is another example that is a bit more than conceptual and shows you the power of all this. What is the power of really watching something while it emerges and not afterwards? So here we have lead titanate, which is also ferroelectric, while it grows on 2 different substrates. Strontium titanate without strain, and then you see while you grow your film, this frequency doubled signal increases. So apparently your film gets thicker, so more polarized material, more signal. But when you grow it on dysprosium scandate, which is exerting strain on the lead titanate, then you see it also starts with an increase of the signal, then a decrease, and then an increase again. So something happens during the growth. And if you analyze this in terms of the polarization of the second harmonic sill, then you find what happens is this one grows as an out-of-plane polarized film all the time. So this black curve. The red curve, it starts the same way. So you get out-of-plane polarized lead titanate. At some point that gets unstable and you flip the polarization into the plane. So it's lost for this signal contribution. And it's not that from a certain point onwards you grow in plane. You really have flips from out of plane to in plane. This is why you lose signal here, and it does not just stay stable. And after a while, this stabilizes into a multi-domain pattern that then simply increases again in thickness, and that's when you have your other rise again. So when you do this after you grow your film, you just see it's multi-domain. How did it happen? When did it happen? You don't see. But here you really see it happens here at the, let's say, 5th to 10th monolayer. And knowing that, you can either stop the growth or you can do something against this multi-domain flips. So that's really a power of the technique. It's in situ, not afterwards. That's the lab that we used to do this. So it was funded by a big European project, and it's also big in size. So it basically fills the entire lab. All this is laser. And here we have the pulse laser deposition system. And of course, this is nothing you would like to sell to anyone. The challenge was to convert it into something that is handy and also easy to use. And that's what we came up with. That's what we present now. So a simple, small kind of unit, or 2 units actually, one for laser excitation and one for detecting the frequency double light, flanged onto our PLD chamber, size of a shoebox. I'm not going into more detail here. You will see pictures and how it works afterwards in one of the next presentations. But in any case, we shrank it in size. It's handy. We have programs that make it usable for non-specialists in nonlinear optics. So it should be something that is nicely, very, very convenient to use in any lab. Just as my last slide, that this really works. So if we take our shoebox-sized detector excitation and detection unit, and we apply the same thing to the bismuth ferrite, as before with the big laser system, we see very nicely how you have the emergence with growth time, in this case, an out-of-plane and an in-plane polarized contribution to the bismuth ferrite polarization. You have a very neat, almost noise-free polarization analysis that tells you how it grows. So like in stripes, we will come to that afterwards. So it's not just an idea or some prototype or something put together, but it's really a working device that we have in our lab. All right, and with that, I'm done with the scientific part. Thank you very much.
So good morning, everyone. My name is Jannis Lehmann, and I'm going to present you in the next few minutes the features regarding our hardware and software that gives you a nice user experience and that leads to a confident data acquisition. And so as Manfred already showed you, so our setup is basically built onto 2 optical setups encapsulated in shoebox-sized boxes. And let me briefly start with the excitation unit, which holds our pulse laser. Here we also have the option to change the incident power. We can control the polarization very finely with sub-degree resolution. We can set from the factory out our focus. So whatever the size of your chamber is or the experiment you want to drive with, we can control that the focus is on the sample position finally. And we have a nice feature that gives you illumination and imaging of the sample in the chamber, so that you can directly see if the laser beam nicely hits the sample that is mounted on your heater. And then here we have our process chamber with the sample. The sample, as Manfred introduced, generates second harmonic generation, second harmonic light, which is detected by the detection unit, the second box attached to the chamber. And here we have many features, for example, an alignment control that we make sure that we have a good pointing onto the detection unit, and also that the light travels through the optical system as it should. Then we have multiple filtering methods. So we have spectral filtering, we have spatial filtering, and finally also some temporal filtering on the detector. And similar as in the excitation unit, we also have polarization analysis and polarization control for the second harmonic light. Now, currently, the setup looks reasonably bulky. It's a lab prototype in operation since 2021 at ETH Zurich. So here we also have our excitation unit and the detection unit attached to the chamber in a currently 45-degree incident and 45-degree outgoing beam geometry. And the final prototype that we want to put on the market should be much smaller. So here's the sketch how it will look like. So we implemented few degrees of freedom in order to make the beam alignment proper. So here we have an XY stage with which we can control the position of the box with which the laser hits onto the sample. And underneath of both boxes, we have tip and tilt stages that allow to control the angle. Sizes and dimensions, the length of our box is currently roughly 300 millimeter by 170 millimeter by 120 millimeter. Detection unit is a bit larger, 300 millimeter by 200 millimeter by 120 millimeter. And both units can be attached to any type of typical vacuum flange. It can be a CF, so our current version uses CF63, but it can be also adapted to any other vacuum flange, CF or KF type. So then let me come to our software. So the back end is currently up and running, and it's completely terminal based. So with the normal terminal input-output system. And the user interface that we are about to develop with an experienced partner, I will show you now. It's a preview how we want it to look like at the end. And it should be based on 3 different screens. One screen should be the startup method. So we initialize all our hardware and we make sure that we have a good alignment. Then the second screen would be measurement or data acquisition and measurement. And the third screen would be the data evaluation. So on our first screen, we can initialize, we can click on initialize, and we initialize our components inside the two optical setups. We can start the thermoelectric cooling of the laser, start the seed laser and the amplifier, choose the repetition rate and an amplitude we want to work with. And the next step would be the alignment from the excitation unit towards the sample and towards the entrance of the detection unit. So if you click on that, then automatically a camera will show a picture of the heater where you can see the laser beam now converted to green light that you can easily see it. And you can see the sample and you can guide the laser onto the sample. And this is particularly useful if you have multiple samples installed and you want to choose a particular one, or if you have a small sample to make sure you really hit it. Then you can also control the power in a more fine way, and you have a screen that gives you the a target on the detection unit. So you see that the laser beam hits the sample by the camera, and then it goes to the detector, and on the detector you have this screen, and you can manipulate the detector X, Y in order to make sure the beam hits the center here. So for the camera, you can play with an illumination. So there's also some lighting that you can see the sample. You can play with the zoom when you want to see it more clearly where you hit the sample, and you can play with the gain. You can go to full screen and also reset your screen, of course. Next step, when you hit with a laser the entrance of your detection unit, is that you click on a line through the detection unit, and here our detector will show the intensity of the green light, strongly suppressed, of course, otherwise we will destroy the detector. And here you can see the intensity read by the detector. You can play with the window size that you can tune it. And now the idea would be that you play with the tilt and the tip in order to make sure that the light passes nicely through the whole optical setup. Finally, you can choose an iris size as small as possible that you don't lose any intensity from the detector, and then you are ready to go for the final measurement. And the final measurement is on the second screen, the data acquisition screen, and here you can select measurement mode, and I will quickly show you how such a mode can look like. So you have some input options here. You can set the user, you can set your sample that you're about to grow, and you can give the growth conditions. So for example, repetition rate of your PLD laser, of the excimer laser, pulse energy of the excimer laser, oxygen gas pressure, temperature, and so on. And then we have a set of predefined scripts that you might want to use for your measurement. So one very obvious one would be the time trace. So you can drag and drop time trace to the sequencer. You can define the polarization and analyzer position. So polarizer means the polarization of your infrared incoming light, and analyzer means the analyzed polarization of the converted green light. And you can set the step size for your measurement. Then after the growth, you might want to confirm with an anisotropy measurement how the distribution of domains might look like or how your growth went. And therefore you can check the anisotropy. Here you can define a relative angle between the analyzer and polarizer and give an angular increment. And there's also polarizer measurement where you only rotate the polarizer at a fixed analyzer position, rotate the analyzer with a fixed polarizer position. You can also measure a full two-dimensional map where you change both subsequently the polarization state and the analyzer position, and then you have a two-dimensional polarization map, or you can basically monitor just the infrared reflectivity in case you have, for example, a metal to insulator transition. Depending on your thickness or temperature, you could go just for the infrared reflectivity. Then after dragging and dropping the desired measurements into the sequencer, you can click on OK. And then you can choose the representation if you want to have a polar plot or a Cartesian plot or a two-dimensional map plot. You can click on autosave after completion, stop the measurement. Then a feature, for example, if you want to indicate when you started your excimer laser or when you change the temperature, you can add markers that are at the end in your data set. And while you measure, you can also open a measurement from the past and compare two data sets. So here you can also choose again between polar, Cartesian, or a map plot, and then you can confirm if the growth is as expected. So the third window is the data evaluation window. And here the idea is that you click on open measurement. You open, for example, a two-dimensional map where you have a polarizer angle plotted from 0 to 360 here, and analyze the angle from 0 to 360 here. And you can normalize the data. You can search a crystal database. You could also select a point group. When you click on select point group, you would have, for example, a pop-up where you can choose, okay, I want to have an orthorhombic system, MM2. You can click on that. And based on your choice, you will have a window that shows you the simulation based on the selected point group or selection from the crystal database. Then you have the full interaction matrix for the second harmonic response. And here you can have sliders where you can play with the actual amplitude of each individual component, which will also directly alter your simulation pattern. And then at some point, if you are happy with the matching or the visual matching of your measurement and your simulation, you can run a fit, and then it will take your input data as an initial parameters and simulate what the actual outcome might be. Gives you also some difference and then you can show the results or save the data. Right, and that's it from my side.
So yeah, as my colleagues Yannis, Manfred and Morgan explained, the system is running in the lab. It's fully operational since 2021, so it's going in its 5th year now. And in our experience, it has been very easy to use, so it can be operated by researchers and students without supervision of a dedicated expert. It has a robust software, so the software runs stable in the daily use. At the moment, the software is focused on the back end, meaning the interaction with the different equipment, the different devices in the system, and at the moment it's terminal based. So that's the thing that we want to improve with the graphical user interface that Yannis just showed you, and that user interface would provide you a lot of very useful features for this measurement scheme, and support you also then in the analysis. Now, having the system running in the lab, we want to go to an industrialization process, and that is basically the function of Markus and me. So we've been working in industrial companies in different roles for many years. And we will look at things like the mechanics and the housing, make it robust and user-friendly, also having in mind later servicing events. We will work on the graphic user interface, make it intuitive, make it visually appealing, and then also go into the deep depth of the software. So setting up the software in a versioning system like Git, making sure that we have all our unit tests in place, that we have error logging, that we have monitoring, and that we get the software to a reliable status that you would like to have as a customer, and that you don't have to worry about the system crashing during your measurements. We're working on the usability features, so we have also reviewed with Yannis the alignment process. We are setting up in illumination so that you can properly see the sample and overall simplify the operation. And finally, as it's becoming a product, then it's also important that we adhere to the general requirements in terms of certifications. So, for example, a CE certification, and that we make sure that it's compliant and market ready, so that when you purchase it, you don't have long discussions with your purchasing department about the missing certificates. So we think that, with this technology, we bring you a very, very exciting and powerful measurement device to your labs. And as you've seen in the presentation, I mean, especially the online monitoring and the ability to control your growth, I think that's something that really makes a big difference, and that changes the way that you can advance your science.